All right, let's keep working on this. So we can, the second expression for Vp can be found inside of this rigid body PA, and the relationship of this equation can be found in chapter 2. So Vp equals Va plus omega Ap equals Rp slash A. Here, omega Ap is one of the unknowns we need to find, so we don't know this. But this precision vector can be found out by using the given length. Okay, Va is 0, this is a fixed point, so it's 0 plus omega Ap. Omega Ap is angular velocity, which should be on k direction only. This precision vector, it's pointing from A to P, so the precision vector gonna be negative I. And here's a little bit tricky because seems like we don't know what's the distance from here, from point A to point B, because that is the I direction precision we need to use to identify the precision vector. However, we do know and think the y distance here is yp. Sorry about my drawing there, but the drawing here should be, so this bar is connected to this AP, and so we know the y direction, which is yp. We know the length of the bar, which is L. Let me redraw this. This looks terrible. Okay. Point A. Okay. Yeah, now it looks better. Okay, so the distance here, this length, let's call it x, can be found out by using relationship inside of a triangle. We know this length is L, we know this length is YP, and we can find out what is x is. For x, it should be square root L squared minus YP squared. Here we should put negative square root L squared minus YP squared. That's on I direction. And plus YPJ. Okay, here I want you to pay extra attention here. When I write this precision vector Rp slash A, I use big I and big J. The reason I use big I and big J is, if you look at this rigid body OP, it's inside of this our fixed reference in our fixed frame. The fixed frame used the coordinate system big I and big J, big X and big Y. That's why when I write precision vector for Rp slash A, I used our fixed coordinate system. All right, let's keep working on this. Let's do the cross product. K cos I would give you J, positive J, so here we end up with omega AP times square root L squared minus YP squared. And that's our big J. And for the second term here, K cos J will give you negative I. So we have negative omega AP YP big I. Okay, now we can see that VP is written in a vector in terms of big N plus big J. Let's rearrange this. So let's put I in the front. We got AP Y, oops, YPI plus negative omega AP square root L square minus YP square. That's our J component. Okay, so far we end up with two expressions for VP. One is here, VP equals small something small I plus small j. Another expression we got is VP is equals something big I plus big J. And what should we do? How can we use these two equations to find out the unknown? For example, VP dot here, or omega AP. One way to do this is first you understand VP and VP, they're the same velocity vector. If they're both VP, which means on the right hand of the equation, this part is going to equal to this expression. But do not equal all the I and J components just yet. And because here we use small I, small j, big N, big J, means they're inside of different coordinate systems. If we come back here, one's inside of the moving frame, small n, small j, and big I, big J is in the fixed frame. And fortunately, at this moment, both big J, small I, big I, they're on the same direction. So we can see these two coordinate systems, they're same, they're interchangeable at this moment. But keep in mind, if this system rotates in a certain angle, if this small I would have an angle with this big I, and you cannot assume they're same. You have to find out the angle and do the conversion between two coordinate systems. Okay, but for this problem it's easy because they're at this special angle. There's no angle between small I and big I, therefore we can assume are the same. Okay, so once you have this assumption, this two coordinate system is interchangeable, at this point we can equate the I component and J component. Here I used big I and big J. You can use small I and small j as well. So for I components, we have I components from each expression. I components, then we can end up with the expression is negative omega AP YP equals negative omega YP. Yeah, from here you can solve omega AP, which is equals omega, and omega is given, so it is negative 0.4 radius per second. Oops. Okay, that's what you can solve from the I component. Let's look at J component. We have negative omega AP square root L squared minus YP squared equals YP dot plus omega B. Alright, from here, this YP dot is our unknown. We can find an expression for YP dot. YP dot ends up equals negative omega AP times L squared minus YP squared minus omega small b. If we plug in all the numbers, we will find out the YP dot. It's about 136.08 feet per second. So that's the speed how fast the particle P is moving inside of the slot. And right, that's how you find out the omega AP and YP dot. And we still need to find out what's the acceleration, angular acceleration of AP, which is how fast this bar AP is accelerating when it's rotating. In order to solve that, it's pretty similar with the process we did for the velocity. So what I want you to do is, I want you to try to set up two equations for acceleration instead of velocity. You can set up the first acceleration equation by using the equation we learned in chapter 3. And then you will end up with the expression for AP. And then I want you to look at the rigid body PA and use the equation, acceleration equation we learned from chapter 2 to find out another expression for AP. Now once you have those two equations, can do something similarly here. Use this assumption, I equals small I, j equals small j at this moment, and you can break it down to I component and j component to solve unknowns. Alright, try it yourself.